Welcome to this video in the series on the road to quantum reality. In the last video, we were able to show real-wave quantum mechanics' relationship with special relativity, and more importantly for this video, we finally managed to establish the scale for real-wave quantum mechanics, with the wavelength being the Compton wavelength. This means we are now in a position to show how real-wave quantum mechanics incorporates what normal quantum mechanics has to call intrinsic spin. Recall that early on we showed this animation for four waves in phase direction correlation from north, east, west and south. We found spin cells forming at regular locations, but overall the spin angular momentum was zero because equal numbers of cells had opposite rotational directions or spin. So how can we calculate the total spin angular momentum of a structure? I must confess that this has been difficult for me. I can tell you what I did and why I think that it's reasonable, but I'm not entirely sure of its validity. If it is flawed, I'm sure somebody will tell me why soon enough. The first stage is to calculate the location of the centre of mass for a single cell as a function of time, regardless of the actual value of the masses involved. Next, we take psi conjugate times psi as the indicator of the mass involved in this local spin. And this gives us the ability to calculate the angular momentum of that single cell. So finally we can sum the angular momenta over all cells to find the spin angular momentum of the entire structure. The only model we have to which we can apply this procedure analytically is the four-plane wave model, but this is not as limiting as it might seem. Why is this? The opposite spin feature only arises because we have taken only four waves in a specific orientation. If we had many sets of four waves, each with a slightly different orientation, by which I mean the cross is rotated, the opposite spin disappears and we get this animation. It is going to turn out that the centre of mass moves in a circle. The symmetry of the situation would make it thus anyway, so adding each and every new set might change the amplitude, but it will never change the radius of the centre of mass. So, how to find the centre of mass? Well, the waves are pressure or density waves in this presumed ideal medium, and a density variation can only arise from the movement of some mass. But we don't know what the rest density of the medium is. Can we just ignore it? Imagine that we are looking at a lake whose depth we don't know. When it is calm, it has some equilibrium level on a measuring stick attached to the bottom of the lake, but we don't know how long the stick is. If we now observe a wave, we can say that it has to have resulted from the motion of some amount of water, so we now have high spots and low spots on the surface. The amount of water that has moved does not depend on the depth of the water. In fact, we can ignore all the water below the lowest point the wave reaches on the measuring stick. It's as if it didn't exist. Now, in the present situation, we are not talking about depth, but density, and we don't know what the equilibrium density is. So we don't know what changes to the amplitude will result from the movement of a certain amount of mass. In a very dense medium, the motion of a fixed mass of fluid will result in a very small change in amplitude. Conversely, in a low density medium, it would result in a very large change. But actually, we are not interested in these amplitudes as such, because we have already gone down the path of accepting that the effective mass of an FR will be given by psi conjugate times psi. All we are worried about is the form of the waves and what this means in terms of motion of this centre of mass. I have taken this to mean that we can adopt a similar approach to that just described for the water waves. So using the 4 orthogonal wave model, the first thing is to calculate its lowest point over a complete cycle. Then we will ignore anything below this. We are saying that any wave level above this low point represents the amount of mass in motion at this point. We are looking side on at the egg box wave field and see that the low point occurs 4 times in each cycle. It's quite easy to show that this minimum is at -2 times root 2. Now we can calculate the centre of mass as a function of time using the standard procedure. And what we find is that it moves in a circle with radius 1 upon 2 pi root 2. And this is what the red dot was showing in the animation. Now, we cannot do the same thing analytically for our discovered structures, but we can assume that the radius of the centre of mass will be the same for any FR. If we do this, we can move forward with the details. First, we note that for us, the wavelength is not 1, but lambda. So the radius of the centre of mass, rcom, is in fact this expression. Rcom is geometric, so we are just scaling the whole model. Now we can use the standard relationship between wavelength and angular frequency as shown here, and substitute for lambda to give rcom in terms of angular frequency. The distance covered by the centre of mass in one cycle is just 2 pi times this radius, and the time taken for one cycle is 2 pi over omega. So we have the velocity as the distance over the time, which after cancellation is c times root 2 over 2. The general expression for angular momentum in this simple situation is the linear momentum, that is the mass times the velocity, times the radius. So we get the angular momentum of a single FR to be this, which after calculation becomes this. But c squared on 2 omega is a constant for the structure. The total mass of the electron is the sum of all the individual FR masses, so the total angular momentum of the structure is just this total mass times the c squared upon 2 omega factor. For real wave quantum mechanics, we have already established the validity of the de Broglie-Einstein relationship, namely mc squared equals h bar omega, as the correct scaling for our structures. We can substitute mc squared with h bar omega and then cancel the omegas to get the total spin angular momentum of the electron structure to be h bar upon 2. In real wave quantum mechanics, spin is not in any way intrinsic. we have modelled it, and its value agrees with the experimental value of h bar over 2. There is something very interesting about this derivation. We started off with a wave field possessing mass without worrying about it too much. Then we treated it just like an ordinary mass in terms of calculating its momentum from its ebbs and flows as a wave. In this calculation, the amount of mass was related to the amplitude of the egg box wave field, not the square of its amplitude. But then we seemingly abandoned the concept of this mass and switched to the mass as being related to the square of the amplitude, which is its intensity or energy content. So what we take to be the mass of the electron structure is simply a measure of its energy content, which of course accords perfectly with the relativistic mass-energy equivalence. We sort of ignore the mass of the medium as contributing to the mass of the particle. It only counts in as much as it is involved in the energy intensity of the FR. But we don't ignore it in calculating the spin angular momentum. If you think I sound less than certain about what is going on here, you would be right. I think bottoming this out is going to be deferred to the loose ends video, which at the moment has a sometime never timescale. I sort of hope that input from others might help to clarify matters. Anyway, in the next video we will move on to look at orbital angular momentum, which turns out to be equally thought-provoking. We find that the real-wave quantum mechanics model, while giving the correct Schrodinger-Dirac values, goes somewhat further than this in interpretational terms. It's going to be one of my favourite videos. Please like and subscribe, and don't forget to tell all your physicist friends.